Next on our short tour of related instruments is lateral force microscopy. And you remember back in lesson 1 I was talking about how the reflected laser beam can move not only up and down to reflect the up and down motion of the cantilever, but also left and right to reflect the torsional twisting of the cantilever. If we look down the long axis of the cantilever, it can twist due to lateral forces, and it's this twisting that we detect with the back and forth motion of the reflected light spot. Why are lateral frictional forces important? Let's just take the example of a brake pad and a brake drum in a car. They're whirring by each other at very high speeds, and as far as a scanning probe microscope is concerned, those surfaces are rough. So the bumps on those surfaces interact with each other, and each bump is a little bit different size and shape, and as they fly by each other, hitting each other, that interaction is very complicated. So there's quite a bit of excitement about the idea of a lateral force microscope, which after all is just an atomic force microscope with quadrant photodetector, putting that in contact with a surface, moving it by, studying the friction, but now you only have a single point in contact. This might lead to fundamental understanding that will help in the future, maybe a more effective brake pad, or the opposite situation where you want low friction instead of high friction, as for example the cylinders in the engine of your car. Example: here are two topographic on the top row, two lateral force on the bottom row images of an exfoliated compact disc, such that the interface between the polycarbonate substrate and aluminum is exposed. Not all of the aluminum comes off, and where you see it remaining here are here, and here. The images were taken such that on the left we have the forward images, meaning the data acquired when the tip was traveling left to right, and on the right the reverse images, meaning the data acquired when the tip was traveling right to left. You can see the bits here. In fact, you can see evidence of bits in all four images. Those are depressions in the polycarbonate, the ones and zeros of your digital music. Now, the topo images look just as you would expect. In cross-section they would look something like this, with polycarbonate on the left and aluminum on the right. The lateral force images, they're different. Let's take a look at those. If we plot the lateral force voltage as a function of x position, which, if you do the proper calibration, is the lateral force itself, what you would get on the forward image is, if we were to look in close detail, we would see a little glitch as startup artifact for friction. Then we come to the step going up to aluminum. When the tip travels up, it twists even more, and then it comes down and goes onto the aluminum, which has less friction. Then we reverse the direction of the tip, and now we collect reverse data, a startup artifact for static friction. Then we go down a step, the tip temporarily stands up more, and then go on to the polycarbonate, which has more friction. So you see, what happens here is that in these friction loops, we have an indicator of what the friction is by the difference between the forward and reverse directions of the friction loop. Let's label this as a friction loop. And I should also note that when lateral force images are taken, the feedback for constant force in the normal direction is still operating. So the vertical force is nominally the same everywhere on the image. We are tracking the torsion or the lateral forces on the tip from the sample. I'd like you to understand why a friction loop looks the way that it does. And in order that we do so, we have to do a little derivation. And in order to make that derivation general, I will do it for the case of an AFM tip on a slope. When one does a derivation, it's always good to state one's assumptions. I'm assuming constant velocity, that the cantilever is horizontal, that there's no tilt in the sample in the y direction, that's the long axis of the cantilever, so that's the direction going into the screen right now, that we don't have to worry about adhesion, and that friction is a linear function of normal force. You might remember this. Friction is equal to a coefficient mu times n, the normal force, where normal we mean here the component of force that is perpendicular to the surface. You might also remember that kinetic friction tends to be smaller or maybe equal to static friction, just as when you're dragging something across the floor, it's harder to get it started than it is to keep it going. What are the forces acting on the tip? The cantilever applies the load, or set point force, but we'll call it load here. It also applies a lateral force that drags the tip up the hill. There's the velocity. The sample applies a normal force as well as a frictional force. What we're going to do is take advantage of Newton's laws. We have declared constant velocity. That means no acceleration, and that means all the forces in the coordinate directions of z and x must sum to 0. Before we get started with that, let us break the normal force and friction force into components and appreciate that this angle theta here is this angle here and that angle there. You can get that from trig. Back to Newton now. Summing forces in the x direction, setting them equal to 0. We have lateral force in the positive x direction. The sign of the normal force in the negative direction, and friction, that x component, is in the negative direction. And similarly, for all the z-pointing forces, they sum to 0. The load is in the negative direction. The vertical component of the normal force is positive, and the vertical component of the friction force is negative. We want to solve for the lateral force because the lateral force is equal and opposite to whatever lateral forces the sample is applying to the tip, and that is what we're measuring. What you get after doing the algebra are two equations, the top one for the moving up the slope, the bottom one for moving down the slope. Note that they're very similar, but they're not quite the same. In the numerator, we have plus the coefficient of friction for the top one, and minus the coefficient of friction for the bottom one. In the denominator, the opposite. First we have minus, then we have plus. I'd like to make one further set of assumptions, and they are that the tangent of the angle, the slope, is not all that big, it's less than 1, and that the friction coefficient is also less than 1. These are reasonable assumptions. When you multiply two small numbers together, you get an even smaller number. The reason why I'm doing this is because now I have a justification for ignoring the second term in the denominator. This simplifies our thinking greatly, and in fact, so much so to the point that it is practical to combine both of those directions, both of those equations, into one equation by putting a plus-minus sign in front of the mu now. The denominator has become 1, and the plus sign in front of the coefficient of friction means up the slope, the minus sign means down the slope. This is very nice. Why? This first term, the load times the tangent of the angle, gives us our average value in a friction loop for any given part of the sample, and mu times the load is the deviation from that average. What would a friction loop of a sample that has topography like this look like? A flat spot with friction coefficient mu1, a slope with friction coefficient mu1, and then another flat spot with a friction coefficient greater than mu1. I'll draw the friction loop down here, x, and lateral voltage, and we'll line things like this. So we start off perhaps with a static friction event, and then we start sliding. Then as we come up to the slope, we realize the average value of the friction is now the load times the tangent of the angle, and then the deviation from that average value is by mu times the load. Then we're going down a step, so there's an event that almost straightens the cantilever up. And then we said this area had greater friction than originally. We stop, we turn around the cantilever scanner, and nothing much happens for a bit. And then we start sliding again. We reach this, and now it's a step up. That's going to make us twist a lot. And then we'll come back here, because we're on the slope. That causes twisting to the left, and then back down here again. Okay. I tried to draw this such that this and this distance were the same. I wasn't quite successful, you see, but those distances are equal to twice the friction coefficient times the load with all of our approximations. And as you see here, the main point here is that this is twice mu2 times the load, whereas over on the left, that is mu1. And the offset, the average value, that is the load times the tangent of the angle. In conclusion, if you understand the features of a friction loop, you'll be able to understand the contrast in your lateral force images.